Einstein said there's something very special about walking and thinking, right? He'd go for walks by himself in order to be able to get further somewhere in the thought that he was stuck on, right? And that was the purpose of the walk. So yeah, the way we usually, or the way I usually start the day is I first try to remind myself to do everything I can easily do to wake myself up on purpose, okay? To get my brain having more volume of thought, right? Processing more blood. So standing up is a first step to that compared to sitting down. The next thing is to try to take on good posture, but the goal of this good posture is to try to deepen my breath. I'm trying to get more breath next time and get more breath next time, and I slowly go up and I'm up for minutes. I'm working my way to get more and more and more oxygen saturated. And the reason is because it's not that you think it's magical to be breathing in that top end way. It's not magic, it's that you believe that if you have more oxygen saturation, that your brain gets to have more literal access to energy. It literally turns you on more. I mean, when you're running, you're breathing high. You're breathing, stretching for as much oxygen as you can. And if you're not, then you'll run out faster than you people who are. I mean, that's what determines how the effort of being able to make it far running, right? You have to be breathing and get as much as you can from the air. Well, same thing for trying to think. If you're trying to be able to get as far as you can in organized thought, you need to first turn your brain on as much as you possibly can. Okay? Yeah. At least make an effort to turn it much more on than you started if you just woke up. So standing's good, getting good posture is good, breathing deep is good, but the next thing is to try to identify if you're having specific places that hurt, right? So normally there are background things. When you're thinking about something, you're ignoring the pain. But if you can actually do something, find something to relax, to stretch, to crack if you have to, right? To make something that hurt less, just take that effort to do it. Okay, that's always ends up being worth it. I usually spend like 10, 15 minutes stretching things to do that. Right now I'm in front of a board, so I'm going to skip it. But okay, but anyway, then I also have a written thought process to remind me of the project. And the project is what? We're trying to very literally spend our effort to end up in better possession of a story that captures the actual effects of reality. I mean, we're trying to get to the end point where we have a correct, completely correct story that actually captures all the real essences of reality, the built-in features, the logic, the rules that apply, right? All of that, we want to be able to gain a story that makes sense of it. Right now, physics doesn't give us a story that says, here's the picture for why everything works. And here, all the measured facts, like the charge of the electron, take your picture and just figure it out from there. We don't have that story, right? That's what we want. If we have a story with that level of comprehension that matches the measured features we're trying to explain, right? That's the tell of whether or not it's an accurate story. Yep. If we have that, then we can use that story, that comprehension of how things work, to then make all kinds of leaps of imagination from compared to the story we're in right now, right? All kinds of understandings of ways to design a machine to do the transforms allowed in physics, because we'll be able to see the inner gears of the structure of physics. All right, so our goal is to do that, and we've been doing this very intentionally all day, trying to get able to have deep, rich thought, spend the whole day focusing on trying to organize parts of the thought that we can better organize than we have before. So that's the major feature, of the major effort of what we've been doing so far. Identifying all the features that we have to explain. Okay, these are all the constants of nature. There's 288 of them. I'll make a little side note if you want to follow this exactly. There's 288 of them, and in the book that I'm writing, I have a little footnote that explains this very specifically. But if you look up in CODATA or NIST for the whole list of constants in nature and count them all, you won't get 288. There's actually a pile of constants that are just mass ratios. So they're dimensionless, but it's like the proton mass divided by the neutron mass. And that ratio is then called another constant of nature. But that entire pile of just mass ratios isn't redundant information. Meaning, if you just take the proton mass and the neutron mass, also listed as constants of nature on the list, okay, and then divided them, you wouldn't be getting a number that was different at all. All the digits would be exactly the same.
This is actually something that I had thought of and was going to ask you about when we were talking about a specific. I didn't sit there and count them, so I didn't know if it was actually 288. But my thought was like, well, isn't some of this redundant? That was my question. Like,
so the list that they have, some of it is redundant, and by redundant I mean literally if you take the other two numbers that make it and calculate the number you get, there are no changes at all. There's redundant ones in their list. There's a few, maybe 5, that don't belong on their list, and they would agree, but they're included for historical reasons. Meaning, if you think of their list as being a list of fundamental constants of nature.
That would probably be a wrong way to think about it.
No, I think that's the right way to think about it, but if you do think it that way, then there are about 5 constants on the list that don't belong. Why? Because they use like little g, the gravitational constant on the surface of the Earth. That one's on the list. That's not a fundamental constant of nature. That's a constant of our specific frame size. Okay. The pressure ones for the atmospheric pressure, they have different ones in there that are just references to Earth and not fundamental ingredients that apply everywhere else also. So in physics, the ones we're capturing or calling fundamental constants of nature are ones that you find here on Earth via measurement, but you would also find exactly the same ones off Earth too, right? Anywhere else where you could set up the same experiment, you'd get the same thing. Okay, so they have like 5 there that don't belong for that reason, but they're included because historically in a lot of equations, like when you do work out equations in physics, you'll use little g because we're modeling something actually on the surface of the Earth. There's another pile of constants that differ from the 288 number. What was it? The redundant ones, the ones that don't belong. Oh, and then there's 2 that are missing from their list that are on my, what I'm calling the 288 list. The 2 that are missing is Coulomb's constant. I don't know why, but for some reason when they did the new update, they forgot to put Coulomb's constant on the list. It's on the last one.
So it sounds like maybe an accident.
I feel like it's an accident, but I haven't gotten a formal explanation for this. I haven't seen any mention of it.
Do like 2 people work on this?
Don't know why. No, I mean, no, the whole code data people are doing it, so there could be some intention behind that. But anyway, I am including Coulomb's constant, and then they don't include, and didn't the last time either, the Planck force. I believe that's the constant, Planck force, which you can get off of Wolfram alpha instead. But anyway, so that's, when you look at that list, find the redundant ones, find the ones that don't belong, and then include Coulomb's constant and Planck force, you end up at 288. Okay, so in short, I just say there's 288 constants in nature listed on CODATA. They would basically agree, I'm pretty sure they agree, Coulomb's constant is still a constant. It's a pretty big one in electrodynamics, but okay. So these are the features that observably, measurably exist in the world. Right? There's lots of ways to observe the world. You can observe the world socially. You can observe the world based literally off color. I'm looking for the colors in the room. Right? There's different things to focus on when you're observing the world. But when you use the measurable features in that world, then you're now looking at a kind of observable that's the least arguable. The one we can't disagree on. It's the same number whether you measure it, or you measure it, or whether I measure it. We're going to get the same thing every single time. This list of 288 constants of nature is capturing the information of all the real built-in features of whatever reality is. That makes it really important, right? Because if you're trying to tell a story about reality, if you're trying to gain access to an understanding of how it does what it can do, then you really need an accurate story of what it is. Really need an accurate story of what it is. So we're coming to a story now that describes a geometry. It turns out that the simplest way you can take the rules of calculus to form a geometry that closes on itself, make a manifold, which means is important logically, because now you can have a logical structure that has a bunch of rules, a bunch of things that apply in the structure, and they're all coherent with each other. We're talking about describing a geometry that defines a whole system of things going on.
Okay.
Breaks into different sizes of pieces that are moving around in different ways, but it's all closed. It doesn't go to infinity, so all the actions eventually add together to turn around and do the opposite actions, and back and forth and back and forth and back and forth. Okay, a lot of fancy sounding words if you don't know exactly what my hand waving meant.
Well, the way that I'm thinking of this is like, you have it's sort of, it might be complicated in a way, but it's not arbitrarily complicated. It's not like a bunch of weird things intersecting each other. It's like one thing that if you define it right, it literally always creates this.
Yeah. So basically a geometry that defines a complex structure. Yeah. Right? So, and that structure itself defines the different available energies or individual components of the structure and so on. And we're tying it to all of these actual built-in features measurably in reality, right? So that means if we end up succeeding in that project alone, what we're doing on the first step is we're ending up occupying a story for what reality is, a geometry for what it's shaped like and what it's doing, how it's holding itself together, and what all the individual features in that geometry are. That story, if they map to these 288 features, literally if there are 288 sub-stories that come from the geometry itself, and they all give us the numeric numbers, at least to the accuracy we've measured so far for each of those constants, then we've got a single story that geometrically connects all the features we're trying to explain. So we completely do not have this story in physics right now. This is the major goal in physics, is to end up with a single story that coherently connects the things that we know are logically connected, which are all the measured features in physics and the rules that connect those measured features. So this is like literally the ultimate goal, conceptually, to occupy that story, meaning for that story to be in your head and have it to make sense, but also visually, okay, to be able to see through the lens of that story. See the features of the world currently around you through a story that makes sense of all those features in it. Right now we don't have a story like that, right? No. We have, these things around me are made out of, if I zoom really far in, a whole bunch of periodic atoms, okay, with a certain sort of frequency and imperfections and so on. And that gives it the features that it has. But zooming out, that's as much as I have, like why the atoms are there to begin with, or why they're holding into the periodic frequency or connecting the way they are, seems like a magic feature that just comes with those atoms. The list of the constants in nature, let's write that out so it's so important.
By the way, if you ever go to Wikipedia and look up like physical constant, one of the ways that it's like in the first paragraph, it describes them as being things that have no explanation.
Yes.
And that is just crazy.
Exactly. That's where I was going. This is the list of the things that we know do exist for sure, and we don't have any idea why.
But literally the way we think we've thought about things to even get to this point is that there is a way that things make sense. So why stop there?
Yeah, exactly. So that's why we're
same thing. Keep going.
That's why we're then can flip the coin around, just like you're suggesting, and say, all right, then let's take these all as the clues. These are the real features of reality. What is reality? Why does it have the rules we've discovered so far impregnated in it? Trying to find the pattern in the constants of nature. It sounds to people as a goal that's so far out there, the chances of you finding it since Einstein couldn't. First of all, it's a ridiculous idea. We have much more accurate measurements of the data than when Einstein was around. Okay, first of all, you can't make sense of data points that only have one digit. Can't see a pattern until you start to get a few digits going. So anyway, we have much better measurements of all these data points that we need to make sense of. Yeah. We're in a much better position. Plus we have artificial intelligence, and most importantly, Wolfram Alpha, right? It's a language accessible mathematics engine. That tool allows us to investigate the data set and look for the pattern in it to a far more powerful level than we can do individually, right? And pen and paper trying to, orders and orders of magnitude, faster and richer. That basically entails learning the individual details of the data set itself. learning what it is you're connecting together, learning what it would mean to even have a story that satisfies your investigation, right? What kind of story is good enough? What kind? Well, if you believe the data set is true, which we do because we have error bars on them also, which means we can even quantify the confidence of our beliefs.
Yeah.
Okay, I can tell you how strongly I believe that and how much I don't, and so on. So anything that's contesting that would be able to have a claim of how much it's contesting it, so you know how much you're mapping to the data set or how much you're not. So there's a way to have an objective confidence level from the data set, so long as the data set itself is matched to different geometric properties of one set, or just to geometric properties. Anyway, that's the story I think that would be most satisfactory, is a single story that told you what reality looks like, what its properties come from and why. So all of its different geometric features, to understand the geometry of them and how they all connect together to close into one system of a simplest, self-closed, stable but differentiated and integrated structure. What we're interested in understanding first the rules for the simplest one possible. Now, it should be a mind-blowing experience at some point in your life to even have that sentence in your head. There's the simplest geometry possible. Wait, now under the constraints that it's going to be a structured, differentiated system and closed on itself, yeah, there is. That's what the insights of geometry take us to, all the definitions of manifolds. So originally manifolds were defined as, let me back up one step before that. Okay. In calculus, Newton discovered a magical tool. He was trying to figure out, how do I describe, once I have a graph of a system, he was really interested in the functions and the power of functions, but he wanted to be able to get more from the functions than he was. Okay, so I have a function that tells you a graph, okay, of something. Okay, f of x equals x squared. But he wants to be able to arbitrarily pick a place along this graph and then figure out exactly how much area is above or below it. But pick any place. There are sometimes certain graphs make it easy to pick certain places and just kind of eyeball it and get it right. But these curves, these smooth curves, if you want to get an exact answer, algebraically precise, for any spot along x, how do you do that? Right? But there's no seemingly obvious way. But his trick was to say, let's pretend that the system itself is quantized. Let's strip it all up, right? Break it up. We're going to exaggerate it as being strips like this, that are this thick for picture's sake, right? But it really means we're breaking them into skinny strips, still strips, meaning each step from strip to strip to strip is the same size. So you're quantizing the axis. This trick allowed him to come up with a way to approximate. You can find the actual area of those strips, right? You can get that. Well, not exactly those strips, the strips that are like this. Right? The ones that are rectangles. So you're gonna have some over approximation. Or you could have done the ones rectangles below. You can choose either way, but then you're gonna get an over approximation or under approximation of the actual area. And the way to make that approximation difference go to zero is to make your strips skinnier and skinnier. Great. Okay.
But not
then we get this idea of infinitesimal, right? Yeah. So Newton gives us the idea of this tiny thing, because we want to be able to make x go real small, make this differential thickness be as close to zero as you can get for a system, meaning your smallest piece of divisibility in the structure, right? But he very specifically said, but not zero. It's smaller than all of the numbers, but it's not zero. Okay, so let's imagine that what we're meaning by that is that it's finite, but very, 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 very small. In the structure of the system putting together, it's a very, very small piece, the smallest piece that is available in it, but it's finite. Okay, that means we still get to use this trick of stripping things up literally. Using this quantization of the dimensions in our logic, our functions that we're defining, okay? Using that trick, even though they're really small, but they're not zero, they're finite, okay? So that means we have a literal quantization picture, and it gives us a way to really accurately approximate, okay, the features like the area underneath this curve. Okay. It also comes with a set of rules. All of calculus itself, right? It's using this trick of breaking things up. Well, the things have to have logical closure. The calculus comes with this whole set of rules that taken together all have logical closure, which means that when we differentiate a thing into a whole bunch of strips, we also have to have them integrated in some way. And that differentiation and integration process in the logic, those operations in the logic, are literal inversions of each other. If you integrate and then differentiate, you end up exactly back where you were. If you differentiate and then integrate, you end up back where you were. They're inverse logical operations of this structural quantization in calculus. Okay, this is really, really important because calculus is the stepping stone from which all of our understanding of physics arises. On top of calculus, Riemann asked, what sorts of geometries can we do calculus on? Meaning, what are the sets of geometric structures, rules, what sort of geometries can you even make that the rules of calculus are all true on? Okay, and then he used the rules of calculus to use that as a restriction to find the geometries, defining what we call manifolds. Now, it turns out that the simplest non-compact three-manifold available is known as the Giesking's manifold. And it's the simplest for a reason that if you're going to form a closed structure, you're making a loop somewhere. And since the structure itself will be the reference, it's going to have at minimum one unit circle. Technically, we're not really making an infinitely perfect circle. We're making a quantized approximation of the circle because we didn't take this all the way to zero. We cut it off somewhere. So you can make a circle out of this with a whole bunch of tiny dots along there, but if you zoom far enough in, there's going to be a straight line between them, okay, a little straight line segment. Okay, so you can have a very high number of dots around the circle approximating a continuous circle, but in a quantized structure, it's not going to be an infinite number, it'll be a finite number. But if you take that argument the other direction around and say, what's the smallest number? Okay, if you want to be approximating a circle, meaning you want to be binding a logical structure under the logic of circular rotation, okay, there's some sort of circular operation in the logical structure. You want that to be in there, but you want to make it with the smallest number of points. The smallest, if we wind down the number of dots that we can make the circle out of, it turns out being 3 is the smallest number. Because when we have 3, we have a triangle, and we're actually dividing the circle into a space that has an area. If we go to 2...
it doesn't have an area.
Yeah, there's no more area, yeah. Okay. It also turns out that this structure is minimal in another sense. The volume, for the same reason, it's calculated off of the same thing. The volume of that hyperbolic distortion is the minimal volume you can make a balanced hyperbolic distortion out of. So it's the smallest possible volume that you can hyperbolically balance into the world. Just as a heads up, we're going to try to build the entire world, the whole physics story very specifically, but we're going to keep track of the quantization. So we're not going to say there's some infinitesimal with, its value is smaller than all other numbers, but not 0. We're going to say literally where the bounds are. In fact, it's going to be 5-dimensional, so there'll be 5 of them.
We have a definition for that infinitesimally small size or something?
Yes.
Okay.
Yes, we have in physics for measurement definitions of the limiting bounds in each measurable dimension. So these are dimensions. So every time we find a rule that connects 2 or more dimensions together, we get to think of them as a prescription that keeps us aware of a rule built into the world. Okay, that's the first thing to remember. So when we look at the equations of physics, like E equals mc squared and so on, that's another one of these rules.
Yeah.
E equals mc squared, meaning we can write it, we can make a graph for what the bound between E and M look like. We get two levels of collecting clues about what reality is that count as completely highest level valid clues, right? You might have gut intuitions about what reality must be and think they count as valid because you've thought them for a long time. But I'm talking about things that elevate to a level of security and confidence that's way beyond anything that could come from any gut feeling. Measurements. Okay? That's the thing that determines whether your story is right or wrong, or the measurements. But what we want is to remember that there are these 288 measured constants built into the world. And each of them comes with, even if you don't know it yet, each of them comes with a specific prescription that connects dimensions into the world. This is mind-blowing when you first see that you can use algebra to see into the geometry of what's going on. I don't know if you're starting to see some of it, but we're going to search for the list of facts in physics. Each new fact in physics comes in the form of an equation that connects something real to something else real in a logical way, right? It gives you a function between two different things or more than two things. The things that connect things in the world, the equations in physics, come with constants like c, right? E equals mc squared. That c is important. One of these constants, but the functions that connect the constants are the rules in physics. Okay, so we want both things to keep track of: the constants in nature and what they do that connect certain logical statements into the world. Okay, and then we want to eventually, we will keep in mind that we're always after a way to visually grasp or entertain the story that we're telling, not just algebraically. Okay, so we're always searching for a way to keep track of the picture of what we're saying. So in general, the architecture of where we're intending to go right now is way at the end goal for me is the vision of being able to literally make universal replicators and holodecks, to have the technology and the understanding behind the technology to be able to manipulate on purpose the arrangement of matter into any form I want. That's the goal at the very end here. That goal is looking straight through a path of understanding. That goal's not going to happen until I aim through this, this semi-foggy understanding of what reality is. Right? That's the picture that you have to get through to get there. You have to literally possess the theory of everything. The story that starts with reality looks like this and these features, the story should be able to continue all the way to, and this is exactly these numbers. Right? These are the features that story of what reality is should, on the first face of it, satisfy. The things that thing can do, or all the, it gets much, much more complex, but the simplest face of it would have to be a story for these. And that story has to obey and be compatible with all the prescriptions we've discovered so far that actually connect certain dimensions in physics, like in atomic rules, expressions of reality. Yeah. Okay, so our wide sweeping goal to get to the technology requires us to focus really on trying to understand reality. And I think the best thing to help us get there is to remember that to understand reality means we're going to take all the data points and we're going to try to look for patterns backwards. We're going to try to find, we know if you give me an answer, it doesn't count as a true answer. It's not completely convincing unless that answer gives me the way to calculate these data points exactly as, at least to the measurement accuracy that we've got, right? It needs to reproduce them and therefore predict them beyond that accuracy. So it should make a whole bunch of predictions. It should map accurately to all the things we've actually already found. Okay, we've got a lot of story to tell there. We're going to be working backwards from the data points to look for any sort of story that counts as a story, meaning explains to us why that's, gives us some sort of structural meaning to the data points instead of just this list of numbers. Okay, That means there's a whole other way to approach this conceptually. You can start from the other direction. Since you know that the goal is to end up with a story that explains the data points, you can step over here to all right, what are the rules for actually explaining? I just assume we're going to get one that does the job, but I want to specify all the specific things that it would need to do to explain. So that gives us two ways of narrowing down on the story that we're really after, meaning we're using the constraints of storytelling itself. Okay, meaning logic. It needs to be logically coherent, and it needs to be able to be put into a logic. We need to understand how it is that any universe could perpetuate itself. That's really what we're after. So on the story end, we need to end up with a story for a self-persistent geometric structure, a universe. So it's an invertible structure. Vertible how? What does it mean to be invertible? What can we mean geometrically by invertible? And what we mean is that the structure itself has details on the inside that are breaking up into pieces and strips, long strings that are all fit next to each other and doing these specific geometric things. All the specific geometric things that are structured on the inside define one of the rules in physics. We're after the simplest possible description of a geometric structure that can self-perpetuate. And on this side, we're after taking the whole list of actual features that the real world has in it and trying to find some sort of geometric, algebraic, simple story that connects them, that finds some way to tell us some more about there. So we're looking for the pattern from the data points, and we're looking from the other side. The best possible story would be a story of the simplest possible available geometry to persistence, right? You want to ask, why does something around? Well, give me the logic for things that can be around. And then we'll ask, what's the simplest of all those things? If there's a logic that gives you, let's say 118 possible things that can be around, then you ask, what's the simplest of them? And what are its properties? Define all of its properties. And if it gives you outputs for all of these features, you will then be at a very, very fortunate position of being able to see now a geometry that matches the measurable features of reality. You're finally in a position for the first time in all of human history to be able to think compatibly with the actual measured features of reality. It's never been done before. Everyone's thought from a framework of reality that was not capable of seeing these things. Okay, so when we get that fuzzy cloud becomes completely unfuzzy, and we can sail completely on to taking the steps to build the actual replicator. What you need to be able to see the inner gears, like literally be able to program them in a computer, know the logic of them, right, and how they connect.
So anyway, you're trying to find the relationships between these constants and then map them onto the geometry that
Yes.
you already have some ideas about.
Yes.
And yeah.
Yes. That makes a real big bridge between the two sides of where I think our goals are being approached. We have the data set looking for a story that counts, and we're also at the same time trying to develop in our own minds, what it means to have a story that counts. A story that geometrically clearly allows you to calculate and understand the connections between and so on, but also predict the values for each of the 288 constants in nature. These are the inarguable features of the world. So the first thing you want to be able to explain there is it. Take them as the fundamental features. Okay, well, we've done that. And what we did is we took, that giant massive list of data points, which is a string of digits. We usually write them in scientific notation, right? So to make them all the same, we're going to standardize the data set by writing them in scientific notation. So it's like 1.372943, and then parentheses 21, and that parentheses, the number inside the parentheses tells you the error on the preceding two numbers, like how well we know the number is now clear to you, right? It's a short form, we're writing it, and then times by 10 to the negative 14 kilograms per meter squared or something. Okay, it's going to have units. They're always going to be in SI units. Okay, these for a very specific reason. The constants in nature are listed in SI units, and if you if you convert them to other units, that's technically not a constant of nature, because the SI units are the coherent bases that hold the logic of the constants of nature. That's literally where we get the bases, by the way. I think of this really funny sentence.
This is going to sound like a dumb question.
Go ahead.
No, I don't think it's a dumb question. I should stop telling myself stuff like that. How did we go from like these kind of less, like how did we go from like, a meter being whatever a meter was to being defined based on things that are more fundamental that we couldn't possibly know at the time that we came up with those?
Great. I like that question. I think you've asked it pretty clearly.
Okay, good. Thank goodness.
Okay. First, let me throw in this little quip for fun, and then let's go exactly on that. The first base is the second. I just think it's funny. You know what I mean by the second? The unit for time?
Yeah.
The first base is the second. Now, I'm even bringing this up because it turns out to be extremely profound to know what the second is. Say the meter in the past is defined as what? Originally a distance from a certain city all the way to the North Pole, right? And then you divide it by, I don't know, 10 million or some number like that, but it was a whole number 10. That's arbitrary. Like everybody who hears that definition thinks, oh, so the meter's based on the size of the Earth? Earlier I was saying that the small gravity constant, little g, is on the list but doesn't belong on the list because it was a constant for the surface of the acceleration on the surface of the Earth, right? That's not universal. You can just not be on the Earth and now it doesn't apply. So here's where it comes from. Here, it's really important to see. This is exactly where it comes from and why most people don't know about it. You don't figure out the definition for the meter or the second or the coulomb or the kilogram or the Kelvin until you first discover the built-in relationships into physics. The relationships into physics are the equations that have an equal sign. Something equals something else in some arrangement between different things. And that fixed arrangement is equal to a constant, right? Anytime you get a constant, I mean, you got some symmetry built in somewhere. And anyway, that arrangement is physically existing in some structure. When you find those rules, let's say as it was historically, the units you were using for measurements started out as random units, okay? They started out as anything practical that you could come up with to make it to use as a unit, first of all, as a measure, right? A foot, good, I got a foot, that seems to work, let's go with that. I can count right away, I don't even have to go anywhere, I can just start counting the number of feet.
What arbitrary measure you started with originally.
Yeah, as long as you were consistent, you could still get the same sort of logic to work, right? Now, that's true, it turns out. If you want to work in feet, you're going to end up having a whole list of equations in physics, and each of those equations are going to have a constant out in front of it.
Yeah.
Okay, and the constant is not going to be one.
They're not. Yeah, no, that's what I was just thinking. Like with the.
Okay, but the mind-blowing thing is that there is a structure available in which the consequence of it is all the bases are one. So at first, you have to get to the level where you're measuring finding the rules, but from measurement. You've seen a built-in rule, but you're using a base that maybe doesn't connect to other fields well. You just have your own measure that you're using as a base, okay? But you're definitely measuring that built-in relationship. All right, but then you go to a different field and you start measuring something in physics now, or something in chemistry, or some property in the world, but you're making a measurement. And the base you have to use, at least one of the bases are in common with the other rule you had. Okay, well, you have a choice of not sticking to the same base. Say you used feet last time, this time you can switch to kilometers. You can pick any inches. You can pick inches as the base instead, right? You can choose to switch that for your second description that you're measuring into the world. But if you want to be able to talk about both of these descriptions at the same time, you need that at least the measure of length to be the same one. Either pick both inches or put both
kilometers or whatever.
Or feet or whatever you want. The point is, once you recognize that you want to be able to collect more and more and more and more and more equations of physics that we're all saying are true at the same time, ones that involve all up to 5 bases, once you do that, then you can swing the value of what's the value of 1 meter. You can define it to be higher or lower or higher or lower. You can pick the definition. When you pick it, okay, and you swing it around and you get the other 5, like the second is another one of them, you can look at the connections in all the logic and you can find the one place where all of them agree to 1. Does it make sense to you? Yeah? Okay, so this by realizing that means there are special bases built into, the second is a special literal physical base and logically real, like geometrically a built-in feature of the minimal manifold. Okay, it's a base built into the logic. If you strayed away from this base, you can pick a different definition that was of different value. You can pick a different word, but if the value of it was slightly off, slightly greater, slightly less, then the logic you have for the whole system needs to pick up new coefficients everywhere. It gets much more complex. The simplest the logic can possibly be is using this base. That's what the definition now of this base is. Originally it was everybody made up their own definition for the bases, and then we got along scientifically and we wanted to communicate together, so we started collaborating on new definitions for each base and so on. But then when we got all the way to SI with all 5, and we have equations that connect different dimensions, different sets of different dimensions, all connected by different kinds of equations measured into the world. When we want to have a system that talks about all of those, we're forced, literally, the equations of physics discover for us the bases built into atomic logic. The second is a literal base that we've discovered by measurement built into the world. And we don't know why, because we don't understand the logic yet. We have the measurements for the features that logic is responsible for, but we don't know why yet. We're still in search of that story. But we do know that the 5 coherent bases, they're coherent because they're coherently structured as part of atomic logic, the rules of what atoms get to do. And all atoms have to agree on those base rules.
I actually have no idea, like, when we started, like, using a second, like, as, like, a unit to, like, measure time with. Mm-hmm. And then the other thing is, why the second and not, like, whatever the Planck time is or something? These might sound like dumb questions, but I just need to, like, kind of go over those.
Good. So you're seeing that there's a value for the Planck time because it defines a boundary for the exchange of time, whatever that is, but there's a boundary there by it, right? A cutoff.
No, it's not a number we never regularly use in our daily lives.
Well, we might in the future.
Okay.
Yeah.
But like me walking
But right
around,
now people don't, yes. But,
yeah.
but right now we're walking around without a story. So if you understood the Planck time, let's jump to there. If you understood the Planck time, I'm going to claim that the 5 boundaries to the 5 dimensions built into the rules of reality are literally important things to understand. Okay. If you knew them, if you understood geometrically what they were responsible for, all the consequences of them, and you had grown up kind of developing intuition around them, then you would be able to make intuitive claims about things you can do in physics and crazy, probably things that I can't imagine doing in this room right now without having to go anywhere.
Have a way to even think about some of those things because it just never occurred to you without that story.
Yeah, and so that's a good thing to notice. It doesn't require you being a super genius. It requires you having access to a story that organizes that much more. Mm-hmm. That's what we're really after. You don't need to be a super genius to understand a better story. Mm-hmm. If it's a better story, you can stay the same level of intelligence, but have access to more things, because the story better organizes more things. That's what makes it a better story. Yeah. Okay, this is really fun. Okay, so I think the general outline might be kind of clear. We're going to try to re-familiarize ourselves as deeply as we can with the leveraged conceptual tool here. This trick for quantizing things in terms of differentials, but the differentials represent the dimensions we're putting in relationship to begin with. And the functions represent the rule between them, and we're specifically interested into all the functions that actually define functions built into physics. The structure of the algebraic equation tells you about the structure of the connection. How did we get to the poster from here? That's what I'm missing here.
Oh, yeah.
So what we did is we took all the data points, started looking for patterns in the data points. How do you do that? Well, first of all, let's look at all the degrees of freedom. We have the string of digits. there's a string of digits. It's just a number, there's a certain number of them, okay? And this one we call right now as definitional, so we call it as exact, which means we assume
everything's zero.
All the zeros from there on.
So it doesn't really matter what's after that.
Yeah, but this is definitionally set. That's not a measured feature. I'm just pointing out the difference here. We did not measure that was definitely zero from there on.
And you couldn't because
We couldn't. We just needed to pick a definition for the meter and the second, okay? This is for times 10 to the 8 meters per second. This is a constant of nature. This is the measured data points, the string of digits. It's got a 10 power that is 8, so it's got a power number, and it's got 2 different dimensions, this one is. Not all of them have 2 dimensions. Some of them have 1 dimension, some are dimensionless, some of them have many dimensions. Okay, but this is a measured built-in feature that we call the speed of light. So what we do is when we take the whole list of all the constants, we notice that all of them have those features. They all have a string of digits. We put them in scientific notation, which means you have 1 digit and then a decimal there.
Yeah.
And then however many you know. And then sometimes we'll have error bars, right? Well, most of the time we'll have error bars, unless it's the set that they used to make the definitions off of, which sometimes changes. Actually, each time it has been a little bit different. But anyway, that's all it really means if it's the definitional one. Usually they have actual error bars because measurements have error bars. But here, there's a thing to keep in mind. When you're trying to make sense of this story, normally I wouldn't imagine myself going out to 5 sigma as still counting for a story. Like if you measured something and reported the error bars, you measure it with your eye, look very carefully, and then honestly tell me the plus or minus on the number you just gave me, right? I would think that being 5 times outside of that was wildly wrong.
Yeah.
I mean,
that's what
2
that means,
maybe.
Like,
That's what 5 sigma
holy
means.
crap.
Yeah. Okay. But the reason in science, in this physics conversation, that well, first of all, let me preface. If you look to see how much they've swung the numbers each time that they've updated the numbers at Codata, okay, then you get some outliers that go way out to 15 sigma differences, which is crazy difference. But usually it's 5, maybe 7, maybe 8, but they don't really swing much more than that. So the reason they're swinging all the way out up to 5 and more, a little more, is that the question of the meter and the second are also this conversation. So when you're making a measurement for how many meters per second, the definition of the meter matters and the definition of the second matters. Yeah. Okay, but we're actually using this guy to get that definition. We're yet not just using it, we're using all the other constants in nature to put together the conversation of these bases. But then we're trying to get the measurements to minimize the errors, right? We're trusting everyone's making their error reports as accurate as possible. People are repeating it in many different places around the world. So we're getting very much confidence in the values we have listed. But now we have a very systematic way of organizing the information. We can compare all the digits, we can compare all the powers, so we can compare all the different dimensions. Now, separating by dimensions can be a powerful thing. Take everything that has meters per second in the constants of nature and put them together and to see if they form a conversation. Also, combining constants of nature to try to single out to a single dimension afterwards. So if you've got meters per second, if you multiplied this by a constant of nature whose dimensions were seconds, then the 2 numbers would combine to make a different number, a different power, but the units would just be meters. You have just leftover meters. Now, the answer might be 1.00000000000 meters. In fact, I have many examples. You saw, I think, you watched the video, right?
I did.
I showed some of those. Okay.
Which video? Because I actually watched like a handful of videos now.
Of the audio reading of the book draft that I have out right now, but just a draft. Anyway, there's several constants of nature you can combine with the intent to cancel out, so to end up with an answer that only has 1 dimension attached to it. It's a way to try to say, I want to make this stuff simpler, right? Make it only 1 dimension, so I'm looking at one thing at a time. So you take a whole bunch of constants of nature and combine them, and you can do that. But there's many ways, actually, it turns out, to combine them to get 1.000 all the numbers we have, perfectly 1, perfectly with all the digits we know, 1, and then the unit. Okay, so what I'm trying to show from that is that the constants of nature and the units themselves are a conversation that completely fit together. The bases come from the logic fitting together the constants of nature. Okay? For the constants of nature, values depend on the measurement or the actual scales or definitions of the bases. So there's 2 degrees of freedom of ignorance happening here.
Yeah.
And so that's why in this conversation, we say historically out to 5 sigma. Okay, now if you look, they've been going out even more than 5 sigma from change to change. Okay. But that's okay. 5 sigma is the goal. We're trying to get an explanation within 5 sigma because we both doubt the definition of the meter in a second at a certain precision. And this actual claim of this number depends on our definitions of those. So there's a level of doubt because of that too. So for 2 reasons, which amplifies our error. Anyway, just so there's our comfort zone. If we have an explanation within 5 sigma, and it's not just my comfort zone, this is a traditional physics level right now. They say 5 sigma, if it's beyond 5 sigma, then you need a better explanation, it doesn't count. If it's within 5 sigma, it does. Now, that's to guide our search. So we can easily now, when we're searching for something, if you find something that's really cool, short, little, beautiful description that means something to you, but it gets the number and it's 12 sigma, meaning it's 12 times just outside the error bars of the measured number, then you can just say, well, sorry, you're gone. I don't have to worry about you being on my list anymore because you don't satisfy being within the error bars. So you know where the cutoff is, and that's very valuable because it helps you sort things into the ones that work and the ones that don't. Okay. And that's to help our search. Now, what we need to do is figure out what are the most clever ways of organizing all these constants of nature to answer questions about them. We want to divide them all. We want to multiply them all. We want to find all the interesting relationships built into them. That's our first step. We have a bunch of puzzle pieces. Let's look for all the interesting relationships these puzzle pieces actually have. If you do that, you find 2 really interesting things pop up. First one is you can find combinations, simple combinations. This one divided by this one squared divided by this one times by this one, simple ones, okay, that yield the bases to every significant digit. Just the meter, the second, the coulomb. There's examples for all of the bases. Yeah. Simple combinations that give you all of the bases, which means the constants of nature are the things that are partitioning under the logic prescribed that this one times this one, or this one squared divided by that one, right? That's the logic of the partitioning. The constants of nature are partitioning the bases. This is the big insight. All the equations here assume a 1. Right? Every function has to be applied to a system. It's got a scale to it. Yeah. Okay? And this is a conversation about the bases. This is very important because setting the bases sets the scales. These data points, it turns out, when you start putting them together, reveal that the bases are part of the conversation. That's the first big step. It's like, oh my God, when I try to look for patterns in the constants of nature and I combine them to find their combinatorial rules, to find anything that pops up that might be interesting just as a clue for where to go. The first thing that becomes obvious is that combinations of a 14-digit number and a 14-digit number gives us 1 and 13 zeros. That's a pretty accurate 1. But then the next step is there are other combinations that give you 1.00000 and then 43529, different numbers after 7 digits. Strangely, you can get all 14 digits right from a combination, or you can get first 7 and then it goes off. And you can find another combination that gets the first 7 goes off a different way.
Well, it's That's really weird if a bunch of them stop at 7.
Yes.
That's kind of weird.
Yes, it's very weird. They get the base right. They literally claim the same value for the base. When you combine them, I think it's 1.00000, and then starts going off for the next digits. Very strange. So that's the first big next meta level clue we have. It took a long time to even get the list of the constants of nature and to have measurements that go to significant digits that had more than 2 and 3. You know, to get 12, 13, sometimes up to 14 significant digits is a lot more information than just 2 significant digits. Okay, which means you can be much more confident that you've matched the pattern when you're done. We started out with random bases, like I said, like some people used feet, and those people even changed it every time the king died, right? Let's measure the new king's foot size, and we're going to make that what we use. Yeah. at first that was totally sufficient. And let me make it very clear. If you're making a measurement and making use of the logic of a measurement, but the measurement is a one-dimensional thing, okay, then it doesn't really matter so much about what base you're using. You're just trying to get the output, and the output's in reference to the base that you invented. So it's just the change that mattered to begin with. The thing is, it's only when you want to make sense of the whole world, and you go around and collect the facts that have been found in chemistry and biology and engineering and all this stuff, electronics and stuff, about how the real world actually works, written down in rules that if you go test, you're going to find the same thing is true.
What was the first definition of a second, or what was the first definition of a meter? You kind of went over that one, and then...
Do you see my book on intuition?
So you're going to pull out a book that just talks about this.
I've written about it, so I want to
Well,
refresh my memory to make sure I give you the good points. All right, so let me just start from here and talking about how we've been keeping track of time. So humans have been keeping time for more than 20,000 years that we know about. Ice Age hunters notched holes in sticks and bones to track the days between different phases of the moon. The early Babylonians, Egyptians, and Mayans devised calendars that told them when to plant their crops and when heavenly events such as eclipses would occur. Eons passed as the sun made its daily trek through the sky, drifting through 13 constellations year by year, and the moon waxed and waned in regular succession. This heavenly dance seemed to suggest that time was a function of celestial motions. So this was the first concept that was natural to them. Okay, when they're aware of these things being periodic up in the heavens.
It would make sense to think that, actually.
Yes, yeah. The heavens, it seemed, were made up of regular intervals that controlled the passage of time. That's an interesting, beautiful way to think. To notice there are intervals, there are things happening in the heavens over and over and over. And that gives us a base for time. Okay? Whatever the period of those actions are. Okay? At least gives you some notion first for a natural thing to base it on. Okay. Our modern fundamental unit of time, the second, was originally defined in relation to the most practical of these celestial motions. You know which one?
I'm going to hazard a guess and say that it might be the day.
Yes, perfect. The solar day. The solar day was divided into 24 hours. The hour was divided into 60 minutes, and the minute was divided into 60 seconds. These divisions had navigational significance. Right? If you're out in the middle of the ocean, and you talk about degrees, where you're pointing and stuff like that, you have to be able to divide up the degrees in accuracy. And this is how they divided it up. For example, 4 minutes roughly corresponded with the rotation of 1 degree, which means the Earth rotates at a rate of 15 degrees per hour. So the stars going down in the west will go down 15 degrees on a protractor in an hour. Okay. Or 360 degrees in 24 hours, right? Okay. Under this scheme, the second was defined, literally, if that's the way you think that's defining time, then the second is now 86,400th of the mean solar day, just because of the 24, 60, and 60. Okay? That was the meaning at that point now. In the 19th and 20th centuries, scientists discovered that the mean solar day is getting longer. This forced them to redefine the second based on something that had a much more reliable period, right? Now you get the period that's changing, you're going to have to switch to something else to define your time off of it. Today, the passage of time is regularly measured by the number of harmonic resonations piezoelectric quartz crystals undergo in common watches. Now, let me make that sentence make sense. You have a piezoelectric quartz crystal. It just means it's a quartz crystal. And you put basically between a capacitor. Okay. And if you put a charge across it, the quartz crystal will shrink this way and get longer that way.
Okay.
Or no, so if you put a charge across it, it'll go the other way.
Okay.
It'll shrink this way and get wider that way. Okay. So you make it just the right size so that it hits the capacitors, and the capacitors then send a charge, and that shrink it. So now it has a gap, no longer hits. But then that structure inside here, the spring structure of connecting all the periodic arranged atoms, okay, then say, hey, there's no more charge doing it to us. Let's go back. So there's a spring response in the atoms themselves that have a certain time to take to do. Because you can model it like a spring constant with the amount of time and so on. You can get a value for it. But the piezoelectric crystals have this nice feature that they can keep doing this back and forth. So the amount of time it goes and then back, because as soon as it hits them, then another charge goes and they shrink again. And it just keeps going back and forth. But this allows you to construct something on top of it that has a ticker, a reliable ticker. Why is it reliable? Because its parts are made out of atomic structures.
Actually, until you actually understand like how literally pretty much everything works, you'll never be completely certain.
Great,
it's constant.
great. So
Because
you're actually pointing,
into it.
why don't I go to something that's even more reliable than this? Now, this was a piezoelectric crystal right now. What we do today is go to the most reliable one of all of them, and it comes directly from the constants in nature.
Okay.
It comes from the hyperfine frequency of cesium-133. I'm trying to eventually get us to build it to the point where you can understand the value of what this thing is. Mm-hmm. I mean, this is a little quip joke. The first base is the second, but this second literally is a logical part of physics, necessary logical part. Now, we only know it to a certain precision, out to the best of our measurements in the constants of nature, because we derive it from those. So we don't know it perfectly, but we know it pretty well. All right, it's exciting to me. It really is, because so we've, in our progress story, we've taken all of the 288 constants in nature. We've been searching for patterns. The first big clue we found was that there are combinations, simple combinations, that give us just the bases. So then we elevate our interest in the bases and realize that the whole conversation of physics and chemistry and on up is really a conversation of how the constants in nature connect the bases, okay, with boundaries, the Planck constants. And then noticing two new rules by combining these just to look for we take these 288 constants as the really important features we're going to pay attention to. These are the puzzle pieces for the puzzle we're trying to put together. And when we succeed, we get an extremely high reward of being able to occupy a mindset that actually understands the constants of nature and can do technologies that will stem from that and so on. But it'll be a different world to be able to conceive of a set of rules or geometric structure that actually then predictably gives you the outputs you're trying to make sense of. It's going to be a much bigger thing to leverage than having a story that can't do that. All right, so we've noticed that we can combine the constants of nature to get the single bases, like to perfect precision. But we've also noticed that that can happen in two ways, where we get all the digits, or we get 7 digits and then start taking a string of different digits. From different combinations, we can get both ways. Another thing to note is that we can get the Planck constants in the same way. We can combine constants of nature. The answer that comes out isn't 1.00000 meters. It's exactly the string of digits for the Planck constants. But whenever we do this, we only get the first 7-ish digits, and then they're different. Find a different combination that can get you to there. The first 7 digits will be the same. If the different constants, though, that got you there, then it'll be different after 7. So this bi-part structure, remember our best measurement goes to 14 digits. Everything, any kind of feature we've measured and set up a lab, and this is, by the way, measured using CERN, right? Our best feature, it's extremely more accurate than what we're doing when we're walking around and just using our eyes and measuring from that. It's very, very accurate, but it's 14 digits. It's the limit of accuracy. For some reason, in the combinations of the constants of nature, at 7 digits, there's this combinatorial glitch. Something changes there. Okay, so that's what we've noticed so far. The bases, the boundaries of the bases, the Planck constants, the combinations of the constants of nature are a conversation about both. And we have this rule that somewhere around 7 significant digits, the structure changes. Sometimes this happens, sometimes that happens, sometimes this happens. It's always after 7 digits that this is happening. So now we don't know at this point in the story why those are the features. Okay, what we're really doing, we're trying to get to a story. So we're noting features, rules that we see built in. So we can write down that rule that it's 2-part. There's some sort of geometric action on the outside, also I'll call it external. on some sort of set of boundaries, also external. So that's our one part, a geometry with boundaries. Okay, we're going to say it's got two pieces. We think of one of them being the geometry, the shape of the piece, and the other one being the parts that it's being made out of. Okay, but then I can multiply that by another part, which I'm going to put as being with the 1 plus, internal. Why I'm doing the 1 plus.
I was going to ask, what does the 1 do here?
And it's also got, well, let me write it that way first. It's got boundaries that are internal. Now, the thing I want to point out first is, before I get to the 1, it's just a 2-part structure. We're saying we have 2 different sets of boundaries, and they can have the same. You can put the same thing here as there, but they could be different geometries. Okay? And then they come together. Now, one more step before we do the 1. It turns out that our B internal is always going to be equal to one very specific set of boundaries in our structure. And this is the thing that's going to be responsible for getting us to that 7 significant digits. That structural feature we're going to try to encode, and we'll say this is the thing, this is the symbol we're going to use, but it's going to be there every single time. In this 2-part structure, it's going to be there every single time. The reason we need the 1 plus is because this thing is going to be much smaller than one number. Okay? And that means we can now combine 2 pieces into a small piece and a bigger piece and have it be a bi-part structure. But this needs to be constructed from Planck constants. And it turns out that there is a Planck length, Planck mass construction. You put those 2 together, you get a certain number, string of digits. And then if you divide it by the value of the Planck charge squared, you get the same string of digits for first, I don't know, 5 or 7 or something. Times 10 to the negative 7. So the digits cancel. Times 10 to the negative 7. This is approximately 1 times 10 to the negative 7. This is literally a scalar that identifies exactly the structural feature we noticed being in the constants of nature, and we don't know why. Okay? But now we're able to write down the general form of that rule that we've discovered. We're just writing down what it means to be like that. We don't know why it's like that yet. Okay? Here's the rule. It's got some geometry on some boundaries, some internal geometry on some internal boundaries, but they will always be this specific set, because this is what guarantees that the scaling changes or some other part comes into play at the 7th significant digit. Interestingly, there is a Planck construction that does that. So we still don't know why. We still don't even know that we're right. We're just following this logic. We found that structure. We found a combination in the Planck constants that matches the scale of that structure we just found. Okay. So we're going to write down the rule and just assume for now that, okay, those Planck constants literally are playing a second component to every arrangement that defines a constant of nature. So we've made a rule now that's put him in here. And this rule has come very specifically just from looking for the patterns in the constants of nature. My point is that we have just a rule that says something very simple. I don't know if this looks complex or simple to you, but it's bipart. That's the first thing it says. It's 2 parts. It's got this part, it's got that part. Yep. One part is much smaller than the first. That's this one, because this number is very small. Then we just need to interpret, what are we allowed to put here? What are we allowed to put there? What are we allowed to put here? To understand what the rule is telling us we can do, or what it's structuring into rule. All right, well, this can be any geometric operation. Anything you can algebraically specify precisely. So pi, there's lots of algebraic recipes for pi. Okay. It could be 2 pi, it could be a 1. Okay, but the simpler the better, because then we can interpret it. But the boundaries need to be the dimensions of the constant. So here we got a constant. We're going to set this equal to a constant of nature. Okay. If we want it to be c, this works for all of them. So if we want it to be c and put c here, then we put this whole string of digits here on this side with the dimensions and everything, and then say that has to be equal to some number times by a set of boundaries defined by the Planck constants and set by the dimensions of the constant itself. So this one has meters per second.
Would be what, Planck lengths over Planck seconds?
Oh, perfect. So
what Planck time?
Yeah. So we'd put in 2.99792.458 times 10 to the 8 meters per second equals some geometry we don't know yet, times by the boundaries depended completely on that, exactly like you said, the Planck length over the Planck time. So we're going to convert, using this prescription, every constant of nature in terms of Planck constants and look for pattern. That's the step we're doing right now. We don't know what's going to lead to pattern at this point, but we have a logical way to proceed because we have a reason to suspect that there's a two-part structure, and we have a reason to suspect that we know a piece that's putting together the two-part structure.
So how do you go about figuring out what this is? And what...
Great. Thank you. First, we note that this guy is times 10 to the negative 7. So it's only going to come into play somewhere around 1, 2, 3, 4, 5, 6, 7 right here.
By the way, is that literally what that number is, or is that kind of just the scale of that number?
It's very, 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 very close. 99999, and then a 1, and then 999.
Okay.
It's very, very close.
That's interesting.
Very interesting. Okay. But what we do is first, we're going to search for this one. Uh-huh. We have these two. Great. I mean, I'll give you the list and you put them in. Now you're able to calculate this one if we just assume that there isn't the second half. So I put a 0 in for here in my head. I think of 1 plus 0 box, which means the whole thing goes to 1. Now we ignore it for now.
Okay.
It's a two-step process. First step is to ignore the right-hand side, which is pretending that's a 0, and say it's all responsible to this. This is responsible for the whole number now. So then you search. Put this number in Wolfram alpha. Mm-hmm. You put in the number for that, divide by the number for that, and times it by x. Oh, okay. Solve for x, and it gives you a number. And then you ask it, what does that number mean? You take off one digit. Well, we know in this case, and it's important to know, we need a number that's not just 2 digits right.
Yeah.
That wouldn't count for us. It's like, we know it's going to be very somewhere around there, but if you can give me this many digits, cool. This many, even more cool. This many, great.
And then
right?
You're looking to see if it like a familiar other number?
Anything you can interpret.
Yeah.
Anything that's short and simple, if it's a whole bunch of things added together with high powers and stuff, you're like, well, look, even if that is the answer, it doesn't count as an answer. It needs to be something that's possible of telling the story in short form. So we're looking for all the short things, and you make a list if there's more than one. Sometimes there's lots. Sometimes you search for a long time without finding any. All right, so in this case, the cool thing is the answer, the number for A, external, turns out to be 1.
Oh no. Wait, okay.
Interesting, right?
Whoa.
1. So then, now we say, all right, we don't even need to write down the 1. Let me write it like this now. It's times the Planck length over the Planck time. 1 plus x times our internal inversion boundaries, okay. These guys. Now we just have to solve for x, right? To find the second half, this part got really simple. I mean, our equation is a very simple representation for this constant of nature. And now we just want to make it all the way accurate. It's like accurate out to there right now. Mm-hmm. And to make it all the way accurate, we're just going to solve for this other next. And we look for the right answer. Anyway, it ends up being square root of the Giesecke constant times J1 minus J2 times by our box. The Giesecke constant. Wait a second. You know how pi is the geometric number that represents going on the unit circle to the other side? It's one representation for it, right? It's the arc length of that circle from there to there. So it's built into unitary logic, okay? Fundamentally, it's a geometric number of logic and geometry. The Giesecke constant is just like that, but for the Giesecke manifold, the simplest possible 3-manifold, okay? Now, this is known, this constant represents something physically real to us. It's the limit of what? The speed of light. We call it that, right?
Yeah.
It's really the speed of space-time, but anything that's going the speed of light, it's the name we give it, the speed of light. Okay, so it's the limit of speed is the big point. You can't go faster in reality if you're constructed of atoms than that speed. There's a built-in bound into the geometry of the relationship between the Planck length and the Planck time. That boundary represents the fastest speed there is in reality, in the geometry of structured reality, okay? But it literally comes from the meaning of speed. It bounds speed itself, right? Coming from the other pieces that make it up. Logically make up the dimensions of speed. All right. But the thing that's binding that fastest possible speed on the inside is the square root of the Giesecke constant. The square root of the simplest geometric structure a manifold can be made into. Okay, there's a constant that represents that geometry. Instead of a simple circle, it's a higher dimensional, but it's a 3-manifold. Okay, so this is a fantastic start to try to read into the algebraic rule that's responsible for this. Now, what are we trying to interpret it as meaning? We have a system by the hyperbolic figure-8 knot, which we found from this quest, this years and years and years of searching, as to be a dominant part of the pattern. When we look into the hyperbolic figure-8 knot, it's got this symbol like this. This is the volume of the hyperbolic figure-8 knot complement, and it's equal to 2 times GGI, twice the Giesecke constant. And this structure represents the minimal possible structure available to calculus, okay, to hyperbolic structures. And it happens to be now related to the boundary that's creating the fastest possible speed in reality's structure. There's a really, really, really nice connection to be making to lead us further and to investigate. I didn't mention these two yet, but this one is a geometric constant that might not be so familiar to physicists. Physicists aren't taught about it. Okay. Most of us, I believe. I'm sure some have been, but it's an extremely important constant in geometry. Okay, and the concept of manifolds needs to be really something we get very, very familiar with.
Yes.
But I'm pointing out that this is the simplest of all manifolds, is characterized by the structure of the Giesecke manifold. All right. Where else have we gone? Well, I kind of jumped the gun and pointed out that after investigating all these relationships for a long time, using this rule that we found from looking at the combinatorial structure in the constants of nature, there's one other rule, the one that gives us these guys, that we got by semi-accident.
Okay.
I mean, I've been searching for it for a long time, and I wrote about it in that book. And somebody contacted me on an email and said, sure you know about this, but just in case. And it's a blog post that somebody had discovered a relatively short and simple equation that gives an approximation of the fine structure constant to more digits than anybody else had ever done.
I read a little bit about this because I kept going. Your thing that you sent me like the first 2 chapters, and I just went through the whole thing.
Okay. Yeah. So you remember that part of the conversation?
I do remember that part. Yeah.
That's the.
I think his name was De Vries. Or something. Yeah.
De Vries' equation.
I remember that because I usually don't remember names. But.
Good job. Okay, well, this equation came from magic, meaning that when I first got it, I didn't have much of an understanding for its power. But here's the thing. The fine structure constant's got this symbol. It's used, let me point out real quick, it's equal to J1 squared, and we'll get to what J1 means, but Feynman pointed out that the one we talk about, fine structure constant, if you take its square root, that's the more interesting number. Anyway, so that would be the J1 in this case. This fine structure constant shows up in the connective logic of the constants of nature in atoms all over the place. More than 100 times. Okay? All over the place. More than 100 times is a lot. There's 288 constants in nature. Okay? It's a lot of times that this guy plays a role, or its square root. Okay? Or sometimes it's square. Okay? And it's really built into the connective logic of the constants of nature. It's dimensionless. Now, I would say, I'd venture a guess that 99% of modern scientists are deeply still confused about the base question. They're still not on board. I'm not the only one that knows this, but I'm saying it's not common to have gone far enough in physics to realize that all the connections and rules in physics force us to these interesting logical bases in the atomic logic. Okay, so most people don't really know that yet. So when they come to the conversation of the constants of nature and they try to first fantasize about making sense of them, the ones that have dimensions, like meters per second, they think, I don't know, that's not really a constant of nature, because I could have changed it from meters and seconds. They don't know that the bases are intrinsically part of the conversation. So, but that doesn't stop them from asking about this one, because it's dimensionless. So for most people at the beginning of the conversation who don't really know the bases are actually part of the conversation, they still get intrigued by this part that can be nailed down. There's no change of coordinates that changes its value. It's just this dimensionless number like pi.
The thing that threw them out about the units that can't possibly apply there.
Exactly, exactly.
So
Exactly. So this one is not only known to be prolific in the story, whatever the story is, it's in the equations for physics and chemistry, but it's also easier to approach in the sense that it doesn't have the confusion of the bases. People have approximated it, try to find ways to algebraically get there, and haven't found much that was interesting. Okay, De Vries's equation, as you found as a review, he got an equation that got like 8 digits, which was phenomenal. It was 3 better than the best from before from a short equation. But his equation has structure to it. It has this 1 over x. I slightly changed it because he was focusing on this and I'm focused on that.
Yeah.
Okay. But x cubed over 2 pi equals I to the I to the negative 4 pi over 8, right like that, minus, oh, he didn't have the minus, just like this. Okay, it was written differently, but it converts equal to this, okay? All right, so this form, compared to every other algebraic arrangement that anybody had ever used to approximate the value of this guy or that guy, okay, got 3 digits better. That's 1,000 times more precise, okay? 1,000 times more precise, but it didn't get all the digits. It's still missing like 3 of accuracy that we have, okay? But because it was the best, I thought, well, what if I just take the right answer, take this number, take its square root, and put that in here, boom, and boom, and boom, the measured one, the best we know of it so far.
Yeah.
Put it in there at the same time, all 3 of those, so that I know that if that number were structured this way, find out what do I need to offset this structure over here by, minus x, for that to work. Whoops, I'm using x's over there, so let's use an a. Minus a. What does a need to be if I put the right number in for x? And the number came out to be of the scale, it says scalar because it's representing mass gap, but the scale of the Planck mass. Okay, this is a really exciting thing when you can find a connection. Now that's a loose connection, to be sure, right? You found something that matched. It didn't explain it first round, you just found a connection you didn't expect. So now we can start to interpret this a little bit though. We can say, all right, this is describing a hyperbola over here, okay, with a 2 pi added to it. It's a hyperbola like this. There, but the 2 pi changes it. It adds a twist somewhere. Okay, so we have a unit hyperbola that's twisted and the whole thing's equal to this for some reason and offset by this value. When we have hyperbolic structures, we always have a mass gap. What mass gap represents is if you have the double cone, this is a surface in the structure of hyperbolic logic. Okay, so this will be a zero boundary of some sort of action that's zero bounded there. Then there's the double sheeted hyperboloid that goes inside that surface in both cases, but that one has a gap from here to here. There's a literal space, a size associated to its gap. And that's gap size, and then there's the single sheeted hyperboloid, which goes around the whole thing. Okay, so those are 3 different logical bounds, surfaces of logic. okay, holding together a structural system. But the size, if I squeeze them together, if I make it much closer, so the gap's only that wide, then the angle of the cone will be much wider. Okay, and the bottom one too, they're going to be symmetric. And I can only go down to the gap touching, and then the cones are like that.
Yeah.
That's the limit, right? So that would be an infinite hyperbolic structure. But notice, I have to get to 0 to reach infinity. If I have any gap at all, then I have a finite hyperbolic structure that it's projecting. Okay, well, if we imagine that this is our general structure, hyperbolic structure, obeying the rules of calculus, then we set our base, we set this gap size to this limit in one of our 5 dimensions.
Yeah.
Which one are we going to pick? Well, we call it the mass gap for a reason. So we're going to pick the limit in mass, and this offsets it just enough to get all the digits. And a little quick offside, this was back in 2014 or so. Okay. And at the time, they were maybe a month or 2 away from releasing a new update, so the data was pretty old. And they got all the digits of the data back then. Now, we're at 7 sigma off, just to throw that out there. However, I still think it's right. I think that last measurement, I've gone through the data quite a bit, and I'm willing to totally make the claim confidently that it's still completely right. It's Zhou 1 that's 7 sigma off, but I use Zhou 1 all over the constants of nature, and all the rest of the measurements, they're not. They're right on. Anyway, I think that there's one new recent measurement that kind of claims to be a lot more accurate, and like another digit accurate than the others, but it goes off quite a bit. And it makes all the other ones very suspicious too. So it's an argument of which one do you want to believe. That one was right in its new different claim from the rest, or the rest of them are right. I don't know. Okay, so this structure, which I want to make it really clear, at this point, we got it because of the email.
Yeah.
Right? We didn't know what it was actually or what it's representing. We need to put it together. We need to figure that out. But we did notice that when we use it and put in that value, we can get the right number for Zhou 1. If I square it, I get the fine structure constant. And so it's mind-blowing because the story we most want to tell, if you can think of all the features in the logic of chemistry and physics, this one's the most prolific. If you can come up with any story for that, then you have a story that's connecting to all kinds of things in the constants of nature. So it's a mind-blowing thing to find anything that could count. Okay? Yeah. No one's ever found that before. So we got a geometric algebraic prescription for a rule. And that rule kicks out a number we very much want, but now we need to understand the rule, right? In order to use it, in order to step on it and build a logic with it, we need to know what it means. So we're going to investigate the rule further. First thing you notice is that this rule doesn't just have Zhou 1 as a solution. It has Zhou 2, Zhou 3, and Zhou 4 as a solution. It has 4 solutions, not just one. Okay? The same exact rule literally has 4 solutions. We didn't change it in any way at all. And those 4 solutions have miracle features. Just those 4 features, those 4 numbers, let me draw them real quick. First one is right here, close to 0, but not. Next one is about here. Next one's up here. And the other one's mirrored down here. They're points on the XY plane. Okay, 2 of them are complex. The other 2 have imaginary components of 0, so they're real. But when we take these 4 partition solutions to this structure, take Zhou 1 plus Zhou 2 plus Zhou 3 plus Zhou 4, we find a symmetry built in, a 0. When we take I never really get sick of this. It's really interesting because I had to discover these piece by piece. I literally had to type those numbers in and multiply them all together and see what happens, right? And this one, 2 pi. Oh my God, this is really exciting because what? Now we're talking about constants, geometric constants that give us a geometric claim of what this guy is, okay? Related directly to pi, to 2 pi, to a circle, to something we know. We'll be able to make sense of this thing, right? So far 0 and 2 pi are things we already know. Very, very interesting. So another thing you do in algebra, when in a system that's broken into pieces and enclosed algebraically, is you want to take the quadrants. So you take the square of all of its components and add them together. Okay. So 2 squared plus 3 squared plus 4 squared. And these, notice, I'm taking the roots, the solutions to the form, and asking what they do in combination. In this particular kind of combination where we add them, we get a perfect balance, a symmetry. In this combination we produce, as a product, we produce a circle. Yeah. In this combination with quadrants, we end up having a quadrant of -4 pi, a projected unit sphere. This is a transform prescription, a hyperbolic transform prescription between a unit sphere and a circle. So it's like a Mobius sphere, the simplest projected sphere you could have because it has one twist on the inside. This to me, I don't know if you're get into algebra, but this is really beautiful. Oh, and there's a dozen more, but these are the first central ones. This one represents what the system is doing when it partitions. This represents structurally how the partitions fit together to logically be bound, okay? And whenever you want to look at, you can have the whole system invert itself, which it's doing all the time, or then you can pinch out an effect somewhere and ask, what happens if I take away one component and just look at these others? Structurally, what other partial sets of structural features are available? Not the full sets. These take all 4. Right? But I can now ask, I have a system that's made up of 4 parts. I can certainly ask clearly, what are the logical parts constructing it that are partial sets of that structure? And you can get a short collection of the partial sets. And those partial sets are all the actual bounds that the constants of nature are on. So that's this one. There's a long story to get around to trying to start explaining J1 minus J2. That's... Okay, I could rewrite this one, J1 minus J2 minus J3 minus J4 equals 0. Anyway, we're taking the sums and the subtractions of all of those.
One thing that I don't really have much of a handle on, as far as this goes, is literally what the meaning of that I is. Like, I know like kind of how you get an I, but I don't understand like what.
How do you get an I?
You could square root a -1, right?
Yeah, good.
And the thing that you get is like some weird thing that we call I don't know.
Yeah, but pictorially, -1 is over here on the unit circle, right?
Okay.
And if you've done one whole power to get there, if you've done one transform from here, and whatever that thing is, it's to a power of 1, and it got you all the way to here. Now you're going to say, well, I want to do the same thing, but to half power. Then you just transform into here. So it's literally, you can represent it as a unit. It has to be a value of 1 in magnitude, but in exactly the other direction compared to whatever your x is. That's all it is. So I, whenever you have an I, it means you have a unit in your system. Okay. Literally, the logic of your system depends somewhere on a unit circle. If you have an I, then the logic, the connection logic of your system depends on a unit circle somewhere. Here we have 2 different I's. Tied to the power of another I, a second one, yeah. Interesting, right? What is that supposed to mean? Short form version is that this is the structure of this picture right here. A twist to a twist. So we got a double twist here to 4 pi over 8. And if we take the total tower of I to the 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 I, that fixed point which lives on the grid somewhere here, you get a first number here is I, okay? And I to the I to the I to the I, you keep them going like back and forth. You spiral in, you make 3 spiraling arms into this towards this point, okay, infinitely approaching it. That tower, the specific point, has, we call it a fixed point. It has a fixed point equation, and the fixed point equation is x equals I to the x. We discovered some cool things about this recently. It's a simple fixed point equation. X equals I to the x. This is about as simple of an equation as you can make. It's got one offset. Okay, but you can see that the number I to the I to the I to the I, on, if you put it in for x, you have an infinite power tower of i's. And now you put I to the infinite power tower of i's, they're going to be equal. Right? So you can see it's the solution to this. Anyway, if you look at the logarithmic or exponential version of this simple equation, then we just get 4 pi's over 8s as being the root of the logarithmic root and the exponential root, both directions. Or if you break up into sines and cosines, then you get 2. You get a 4 pi over 8 in the sine and a 4 pi over 8 in the cosine. So the 4 pi over 8 is this magical division spot for this infinite power tower of I. Okay, so let me summarize some highlights here. We've been spending a lot of time prior to this moment using the measured data points, the constants of nature, to find some geometry, some algebraic logic that's fixed, closed, and responsible for those actual features, for those constants of nature, right? So from both sides, we've been attacking this question of trying to build a story as simple as possible that's actually responsible and predictably responsible for the features we've measured and need to explain. Now, what we want is a fundamental theory of everything, meaning in physics and chemistry, the built-in inarguable features that are built in by the rules that are built in. So almost every rule we have in physics, we don't really have a full understanding for why it's there. So they're not stories, they're not explanations yet, they're discoveries of a feature built into the world. They're mysteries that we've securely identified as being there, okay? Which makes them really fundamentally interesting. So these are the most interesting features you could really focus on, I would claim, because they're the features that are fundamentally built in. I'm trying to paint a picture of where we're at in the process and where we're trying to go specifically right now, okay? We're not trying to build replicators yet. We're somewhere back here in the developing the understanding of the structure of reality that's responsible for the features of reality. Okay, well, what we've done so far is we've identified 2 rules. This one has a structural rule, and the one I just erased, I think, the bipart one, the 2-part structure.
What do you call it, the binomial
constructor? Yeah. They're both fairly simple rules algebraically, okay? Yeah. The binomial constructor, we don't know why it's there, meaning we believe it's there. We believe that there's a 2-part structure in the connectivity logic of the constants of nature because we went and checked and found that over and over and over and over. Mm-hmm. To represent that 2-part structure, we had to pick, well, it always happens around the 7th digit. We find a simple combination of Planck constants that literally land that scale. So we say, let's take them as being the thing responsible for that off shift. Now we build a structure with that built-in off shift, 2-part structure, and take it as a rule for how the constants are fitting together. And at this point, we don't know why it's a rule. We're exploring where that rule can take us, right? But we've just found it to be there. We don't know why. Mm-hmm. Okay. This second rule is much more magical than that. There's a level of magic and not understanding so far in that first rule, just to keep track. In this second one, there's more magic because it starts out from, here's an equation that gets you close. And then we find that we can just modify it simply by another very interesting boundary to get us all the way. When we look at the structure, the content of this algebraic statement, and find that it has 4 specific outputs, and that they have these built-in algebraic rules, now we want to look a little further. We definitely want to look a little further because these algebraic rules define a hyperbolic transform between 2 pi and negative 4 pi with a balance involved. There's something interesting happening here for sure. And that piece right here, this G1 squared, is the fine structure constant. So this story, this algebraic connection here, tells us something right now. It tells us that this transform it's talking about, the one that includes the fine structure constant, also comes with other parts. Mm-hmm. The fine structure constant has 3 other parts in this story, okay? Algebraically, it comes married to them, which means there's much more story you can tell now and check against, right? Check to see if that piece of the story tells something you were looking to be told. So now we're going to check to see if those rules can be attached to all of the other constants, or to make sense of. Remember I said this one connects over 100 places in the constants of nature. So if we can make sense of it, then we should be able to tell a lot about the structure of the constants of nature, right? But if you spend years looking for the constants of nature, to decode each constant of nature using this rule and the other one, just those 2, and you're looking for patterns that obey those rules in each constant of nature, and then find patterns. If I fast forward After finding years and years and years down the line, finding a pattern that puts all 288 constants of nature together for that whole poster. In the pattern, we found one. I started telling this and didn't get to it. The hyperbolic figure 8 knot is a dominant player in the Geeskiin constant. Okay, they show up in lots of places, but not knowing ahead of time what those were, and then look them up and start investigating them. Okay, well, it turns out that the hyperbolic figure 8 knot is not just the simplest closed double covered 3 manifolds, so a system that can close on itself under the rules of calculus. It's not just the simplest one, with also the simplest volume, smallest volume complement. It also is a system. It's literally a structured system that has available to it 288 geometric transforms. Okay, 12 rotational symmetries. You can take a tetrahedron. Its symmetry breaks down into being made of 2 tetrahedron faced the opposite way. So there's 2 of them. You take one at a time and say there's 12 ways to rotate it. 3 times around this axis, 3 times around that axis, 3 times around. Right? There's 12 rotational symmetries, there's 12 reflection symmetries, and there's 2 of them facing opposite ways. So there's an inversion symmetry, which gives you a 2. So 12 times 12 times 2 gives you 288. Literally, this geometry suddenly becomes a perfect candidate for the story that's arranging them all. This is exciting, okay? We could literally just have a geometry whose internal symmetric rotations, the ones that are available to it naturally, are all of the constants of nature. That would be a perfect story. So, pursuing that, hyperbolic figure 8 knot has an equation.
Yeah.
It starts out with I. Oh, no. This is the same I. Okay? And then it has dialogarithms. I don't know if you've ever seen those before.
I saw them and didn't know what they were exactly. I
Okay.
knew they were called dialogarithms, and that's all I know.
Okay.
And then
There's our simple equation that gives you the number for the volume of the hyperbolic figure 8 knot complement, which is the smallest complement that you can structure together under the logic of calculus to form a manifold. Okay? And it's the smallest because this number here equals -1 to the 1/3. 1/3.
Okay.
And this number here is -1 to the 1/2. Right? They're both in there. This is the dialogarithmic one. The one here is in the arguments. So in the arguments, the thing we're breaking up into is dividing the plane into thirds.
And to be clear, this is the same as the cube root of -1 then? Is that
Yep,
what it is? Okay.
that's what it is. Cube root of -1. So if you have I in a system, one thing that's important to remember about I is this is magnitude. That means magnitude. Okay.
Yeah.
How long is it? Ignore which direction it's pointing. Just tell me how long it is. Equals 1. It's a unit. That's the whole important point about using it in a logical system. But it's a unit pointed in a different direction. So very important. Okay. So if we have it, if all we know is that there's an I in our physical system, we have some physical system and I is at least in one of its equations, then it means that somewhere in that system there's a closed unit circle, a logic that closes about a unit circle. That divides at least into 4 pieces. Just having a single I means you have a unit circle and it divides into 4 pieces. All the powers of I will bring it back to 1 and you can keep going, keep going.
So we're a dialogarithm. Or not a dialogarithm.
This one? This one?
Yeah, that guy. Right.
This guy is right here. 1, 2, 3, 4, 5, 6. So it lands on 1 and -1 in different powers. He's right here. But if you take him squared, he's right here. This is this guy squared. And this is also equal to this guy cubed. This is equal to him to the 6th, and so on in between, right? So same with I. This is I squared, this is I cubed, this is I to the 4th. Earlier we were mentioning when we were breaking the circle up, we want to do it in the smallest number of pieces. This third lets us divide the plane. Since it's dialogarithmic, we have to do dividing the plane into the minimum number of pieces that you can divide a circle up into logically. So that's the smallest structure, the smallest triangular logic to divide into and close. Cool. But the only thing it really has in it is these 2 arguments, I and the imaginary golden ratio. We believe we're trying to describe the minimum possible quantized self-persistent structure under the rules, partitioning under the rules of calculus, right? But if it's partitioning, if it's differentiating into pieces, then it's also being integrated. So it does both at the same time, which is what allows it to have a closed logic. All right, so we need to understand that structure, that energy structure, but we need to, first of all, get to the point where we have the concepts of energy structures like Hamiltonians or geometric things that have the complexities of what we mean by energy to begin with. If we back all the way up to why is all of this based on calculus? Okay, one answer is that because we're quantizing things, and that's the insight of what calculus is. We're able to strip things up. We're actually not going to go all the way down to zero or even close to zero. I mean, we're going towards zero, but to a very small number, but we're not, it's not a question of whether there's anything smaller than it. It's an actual physical cutoff for our 5 different quantized boundaries. But that means we have 5 different ways that this story can be told in the structure. The system's held together in 5 different ways that are quantized. Calculus allows the rules of differentiation and integration to be connected, so that the way that you break up into pieces is married to the way those pieces end up arranged. So the integration of those pieces is also set by rule. That means if you have a system that's based on calculus, no matter which way you transform the system, no matter which direction you go, from lots of pieces, lots of little waves to one wave, or from one wave to lots of little waves, in any of the directions you can make those sorts of transforms, they'll all coherently be reversible. So the system still obeys all the rules no matter which transform it's already undergone. At this point, we already have a coherent, very strong pattern showing up in the constants of nature, in the logic that connects all the actual features built into the world, the measured features, okay? Which is super exciting because it means, one, we can reduce all of this information to a far small number than 288.
Yeah.
We reduce it to the 5 numbers for 5 Planck constants, okay, and to the 2 rules. This rule, which includes pi now and I, so you need those 2 numbers now, and the Planck mass was already in the 5 Planck constants, okay, and then our other rule, the 2-part, the binomial constructor rule, which applies to Planck constants again, very specifically, and is allowed to have geometric parameters. That means we have 2 rules that apply to how we organize, how we geometrically arrange Planck boundaries together. Okay, so 2 different rules and 5 Planck boundaries. So we have 7 inputs for our story. And with those 7 inputs, we can get all 288 outputs. That's an incredible reduction. I think it goes even further though when you can show the connection between all 5 Planck boundaries. The transform space made available to this hyperbolic figure 8 knots real conjugate, and let me make that very clear. This is the hyperbolic figure 8 knots dialogarithmic construction. This is the equation for how it logarithmically is put together.
Which,
just repeating the one above, but that's because I want to be able to write one right next to it. Now, if we instead we take the same structure here, and we want to take its real conjugate. Conjugate means we take this negative sign here, this minus that I just wrote, and we turn it into a plus sign. All right? In complex numbers, it means you've mirrored about the y. So we're going to turn this to a plus, and we're going to drop the I. We want the real, which means to get rid of the imaginary part, conjugate, which means we change the sign, of the same structure. And it ends up being 4 pi squared divided by a number. First of all, let's note that 4 pi, which means literally we're making a unit sphere square, 2 of them, in square arrangement. Okay, that's a lot of geometric information, divided by a number, and the number is 288. That double square structure divides up into 288 ways. That's what you get as the real conjugate of the hyperbolic figure 8 knot. Okay, so these are basically two parts of the same story. You get this one, you also get that one. Once we have this system, there's all the transforms available to it. So you can use any of the constants of nature to transform this base structure to something's twisted just right to now hold a symmetry again. Okay, and there's 288 of those available in the system, but if you go to one of them, you're in a slightly different system. Well, if I wanted to find the entire available set of transforms to the base structure, it's going to be the volume of the 24-dimensional unit hypersphere. And this thing is famously equal to pi to 12 over 12 factorial. Okay, but if you look closer, pi, you can think, well, let me translate what this thing means in terms of 2 pi's. Okay, let's assume these are all 2 pi's actually there, and I have 2 pi to the 12. Oh, and I have another 12, 2 to the 12 down here compared to before there. Or I could try 4 pi's. Okay, well, I'm going to do it in terms of 4 pi's. This turns out to be equal to 4 pi over 120, which is 5 factorial, times by 4 pi over the arrangements of 5 things, these are interesting things that are both 5-dimensional in logic of combinatorial things. And then we have a 4 pi over 35 and a 4 pi over 18 and a 4 pi over 32 and a 4 pi over 8. And we barely have enough room. 4, 3, 2, 1. There we go. That's the equation. This is the same thing as that. It's just looking at this in terms of 4 pi's instead of pi's. Okay. But that means we can literally take it as a collection, a product of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spheres. One of them's divided up in 120 ways. The other one's divided up in 44 ways. Exactly. This one's exactly 35. 2 of them are 18, 3 of them are 32, and 4 of them are 8. This 4 pi over 8 shows up the most 4 times. So we call it the controlling root of the structure, just because it's there more than anything else. But you can see this one would be the next candidate for it. The almost controlling root, if you wanted to make that notion up, right? And keep going. Anyway, this one also then on that hierarchy becomes the opposite end. It represents something else at the opposite end. And what is 5 factorial? First of all, we really like the number 5 in logic, because we're talking about a geometric system with 5 bases of measurement to it. So something that factors all the ways it possibly can, that has 5 things to it. So you can call them 5 dimensions, factored in all the ways there could be factored, is 120 ways. Just a mathematical operation of the rules of factorization. And the derangement means that you're starting out with a certain set of things, and everybody has to play musical chairs. Everybody has to move. But you can't stay where you started. So there's no holding still. And so that extra restriction that you can't stay where you started in the structural system we represent as being very similar to factorizing, but we put it on the other side and say it's with another restriction. It also applies, in this case, to 5 things. Interesting. 35, 18, 32, and 8 represent the powers for, well, this one's 44, and 44 is for Planck time, 35 is for Planck length, 18 is for Planck charge, 32 is for Planck temperature, and 8 is for Planck mass. Literally the powers of the 10 to the something, that number each time is a whole number exactly. And this structure happens to have those same degrees of freedom in it, meaning it automatically has waves, it has spheres that are logically bound together into one product, but that they divide up differently. But the ways they specifically divide up include exactly the same quantized numbers as the Planck constants. Now, since we're using, I don't know if I've mentioned already, but we end up using definitions for the Planck constants that are plane waves that are quantized. So we have these two simple restrictions. A plane wave is a two-dimensional wave, and quantized means breaks up into an exact whole number of pieces. The number of pieces end up being these same sets of numbers. If you can convince yourself that the plane waves that we're calling the Planck constants are the literal divisions, the boundaries responsible for the divisions in this complex structure, then you have one home, you have one geometric home for all 5 definitions, which you could think of as a dramatic simplification of your system. So you got one home for the Planck constants, and you got 2 rules for, actually I should have said this. We found it using this rule and the binomial constructor, right? We had 2 rules that led us to the pattern we found. But then when we found the hyperbolic figure-8 knot, we found it was responsible for the number of constants in its universe, and happens to be in our universe the same number. But also, I didn't say that this structure itself is responsible for this structure. So this is the cool part. We didn't know where this came from. There was a big unknown, like why is this it? But now I can break this into the left side of the equals and the right side of the equals and show you how each side is just one geometric modification from the properties made by this one. Okay. You want to see it?
Yeah.
Okay, cool. If I write down again, because I'm going to have to repeat it. You okay, buddy? 1 over the imaginary golden ratio, which I should have said over here when I did it for the other one, but the imaginary golden ratio magnitude is also equal to 1. So it's a unit decomposition. So this structure is a unit decomposition structure. I is also a unit, right? The whole thing is all unit based. Minus, which I think is a beautiful thing. It's like a unit circle. This is unit dialogarithms. Imaginary golden ratio again is right about here. Okay. Since it's on the unit circle, there's a certain number of times that you multiply it. Every time here's to the power of 1. This is the power of 2, but it's the same angle from there to there as it is from here to here.
Yeah.
That's how powers work in angles here on the unit circle, right? Okay, so if you have 1, then it means you have a circle that's divided into 6 pieces. So you want to check all 6, you want to check the whole cycle of 6 in this structural equation to see what else is around. Very specifically because you're looking to see if there's any zeros. Zeros are very important information of your system, but let's just check the things that should also be there. So I can also check the next power up. Think of this as a power of 1, power of 1. This is a power of 2. Power of 2. And I can try it for the next one where there's a power of 3 here and a power of 3 here. Same equation each time, and all we're doing was the power goes from 1, 2, 3, 4, 5, 6. 7 is the exact same thing as 1. So 7 is going to give us that again. Yeah. So if this was working and kicked out the number for that, but you put in there and added the power or changed them from 1 to 7s, it should give you the same number again. In fact, any multiple of 6 after that will do the same thing. Okay, well, their values, cycle, the next one is 2/3 VFE. Interesting, it's related to it. The third one is 0. Oh, we found a 0. Let's be more explicit now since we're saying it's important here. Li2 of that minus Li2 of that, and I is 0. Okay, and then the next 3, if we keep going, 4, 5, and 6, let's see, is negative 2/3 VFE, negative VFE, and 0. Ooh. Our solutions in our cycle are structurally that we make a hyperbolic figure-8 knot. We make 2/3 of hyperbolic figure-8 knot. We make a 0 boundary, This one's the one that makes our zero boundary with the third power in it. Then we make, in the fourth power, makes negative 2/3 a hyperbolic figure 8 knot, which is symmetric to this one. Like if you add them together, they're going to cancel each other. All right? And then we make a negative hyperbolic figure 8 knot. If you add it to this one, they're going to cancel each other. And this is for power of 5. Then power of 6, so 3 and 6 gives us zeros. There's 2 zero boundaries in our dilogarithmic structure. Let's just look at the zero bounds. Li2, 1 over to the 6 minus Li2. These are both of our zero bounds. I'm just ignoring the other ones. Put them next to each other. That's it. Those are the zeros, the dilogarithmic structured zeros associated to the hyperbolic figure 8 knots dilogarithmic structure. Our structure is the first double cover there is. But double covers are something that has one layer and then another layer. But the layers are coherently bound together under some logic. So there's 2 layers to the system, okay? That's the most general way to think about a double cover. The structure here is the first layer. But if you want to make a second layer that you're going to connect to, and don't know what it is yet, the one thing you do know, if this is your first layer, then your second layer should be related to the logic of it. Yeah. In fact, the best thing to make your second layer out of is your zero boundaries that you've just made. If the systems specifically connect minimally, the simplest connection is one twist into the system, one loop put into it. So, which makes it, I don't know if you remember the word Mobius. A Mobius connection is like a Mobius strip. Yeah. Okay, so to Mobius strip connect this zero boundary, there's 2 descriptions of it. Let's twist it. Instead of taking these, which are zeros, let's modify the structure by saying, to go from this internal to the outside, all we're going to do is take the same parts and twist them up once. Okay, so we're going to say instead, this one, I can go this way or I can go this way. It doesn't matter when I look at the same equations. So I'll put this one now as a 6 and this one as a 3. There's my twist. Could have gone the other way, it doesn't matter. And both times now we have 2 new equations made of the same parts as the old equations, but arranged differently. Like we literally just swapped components from them. Now they're equal to something different. We get both of these, they're both now true, as 2 independent expressions of what you get from the twist. 2 halves, 2 expressions of the twist. If I combine them, if I take their product, then I times I becomes -1 times negative goes away, and it's just left with 4 pi over 8 to the 4th, which if you remember is the root of our controlling equation for this. Also, 4 pi over 8 squared
is there, yeah.
There's a 4 pi over 8 there. Yeah. Let's connect it more than that because it's squared in the 4th power here, right? So here it's attached to something. It's attached to an I to the I. Okay, now, before we talked a little bit about this I to the I to the I to the I, this fixed point thing. Yeah. Okay, now why I'm bringing that up every time with this is because I want you to think of this as being 2 steps along that infinite power tower where it's responsible for transformations. So it's a transformation that requires 2 steps along that tower. Okay. So it's just a piece of the I, a smallest piece that counts that's plural, I guess. But then that thing, it had an equation for x equals I to the x. Or you could say log of x equals 4 pi over 8 times x times I. Same thing. They're both true, but when you write it in terms of logarithms or in terms of exponentials, you see right away that there's a geometry that counts as the root of the structure, and it's 4 pi over 8, okay? In both e and log ways. So there's 2 ways you can go. This one's going with them also. The same exact structure here is married here, but why is that interesting? Because if you're thinking of transforming along that power tower, 2 steps along the eye to the eye to the eye to the eye to the eye connection, then this happens to be raised to the power of what? To the power of that connection's root. Does it make sense? Did you see that at all? There's a connection, but if you think of this as not just the 2 pieces, but it's 2 pieces of the whole tower that they're structuring, that something's structured together by, then undergoing a transformation raised to this number means you're doing 2 steps along the power tower raised to the geometric root of the logarithmic structure of this whole tower to begin with. It's not a disconnected random power. It's the only one that represents its geometric root. Okay, but this was for the eye to the eye to the eye to the eye to the eye thing, right? You put them in the x's there, put them in the x's here. Okay. So this is a fundamental algebraic way of unitarily connecting or transforming a system into a hyperbolic structure with this specific size of a gap. But unitary in the sense that this is a 1. This is a 1, just pointed in different directions, right? Yeah. But it suggests the dimensions of the system, but also along the eye to the eye to the eye tower, if you're making a stability out of that, the thing you're transforming to is by being raised to the root of your own system. That's this piece right here. This piece turns out to be equal to, so let's write it very clearly, I to the I to negative 4 pi over 8 is equal to e to this, 4 pi over 8 squared. So we take something exponentially, we take it hyperbolically, exponentially, hyperbolically, the same thing, to the boundary that we made when we twisted our hyperbolic figure 8 knots 0 boundaries up once. So what I'm claiming is that twist is the logic for how we're connecting the inside to the outside. The outside's bigger, it has space to make another rotation, and then we connect. But we're making it out of the same pieces, so we connect under the logic that literally twists or transforms the zeros in the existing structure. Okay, on the other side, let's go just the left side of the equation. If I just take the 1 over x plus x cubed, this is an equation for a hyperbola. Its highest power is 3, so it has to have at least 3 roots or solutions. Turns out it has 4. When you check for roots, you set equal to 0. Now these are the zeros we used to be here, okay? Check for roots, we set equal to 0. Now this is a different equation than this because of the 2 pi, right? This is not divided by 2 pi yet. So this is a simpler version, so a reduced form, where we transform 2 pi to a 1 and ask this simplest hyperbolic structure, what would its roots be? And its solutions are the imaginary golden ratio, 1 over the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. And the roots of this simplest projective hyperbola are equal to the arguments in our dialogarithmic structure made by the hyperbolic figure 8 knot. Because these are roots of unity, we have to check all of its powers. It comes with cyclic powers. Okay, so we have to check them all to understand more about the structure that's available from achieving this. When we do, we find 2 zeros. If we take both of the equations for those zeros and swap out 2 of their components, either this side or this side, then we end up getting these equations, which algebraically are very beautiful and simple things familiar to all of us. Their product ends up being exactly the root of the 24-dimensional unit hypersphere, which is nice. But that connects all the stories algebraically.
I do see those connections even if I don't fully.
Yeah. That's all I was pointing out, really, that we can directly connect the structural equation of hyperbolic figure 8 knot, one of its features to one of the features of this, okay? That's great. We can directly now, in a different way, we're looking at this other side. Oh, and that feature is directly connected to, we have to e to the it, but just with that one modification, to the piece that we're using in our main transform equation. So we have a direct connection between the hyperbolic figure 8 knots structural rules, and this is hyperbolic partition equation structural rules, which is nice. So this piece right here, not this piece, this piece right here can be directly algebraically connected to our zero bound, which is beautiful. But on the left-hand side, we're looking at it without this first, just to make it simpler, okay? And say this is the simplest hyperbolic structure. Set it equal to 0, define to solve for its roots, ask Wolfram alpha, and it spits out these as the answers, which we're excited about because these, as being the roots, the thing that holds the structure together, the pinpoints for it of this structure, are the projective arguments in our dilogarithmic structure that we were making this one with. So we're very familiar with those roots. So we're connecting now these two geometric expressions, outside, inside, okay, to being bound under two different rules that are sharing in symmetric ways. This one is used as an argument, and this one is used as a root. The same center, the imaginary golden ratio. Okay, but then we're modifying this connection, just like before when we had zeros. Now we're taking a twisted zero. So instead of having these equal to 0, erase that. So this is our equal to 0 equation. Yeah. Now we're going to swap it, and it's going to be equal to something else. It happens to be this over here, or e to that is the way we're going to transform though, with a gap. But still, it's going to be equal to something else. Same thing over here. When we divide by 2 pi, now our 0 is going to become something special. It's going to become a twisted 0. So that has to be represented some different way, but still, that's basically the story. The untwisted version of this is directly connected already projectively to the hyperbolic figure 8 knots dilogarithmic arguments. That's fantastic. By the way, it also uses 6 of them exactly, which is kind of significant. There's one here in the numerator, one here in the denominator, 2 in a numerator, 2 in a denominator. Altogether, that's 1 above, 1 below, they cancel, 2 above, 2 below, they cancel. That's one way of canceling, but if you also just put them all up top and multiply them together, that would be 1, 2, 3, 4, 5, 6. And this one to the 6 equals 1. So it's like a simple symmetric way of breaking up 1, even in the product sense. But okay, I love the symmetries that are all over in this stuff. Okay, so in general, we have this structure which we can connect to this one. With one modification, then we divide by 2 pi. We go from these numbers that started out from our center to now our j's. Je1, 2, 3, and 4. Literally, instead of this one, this becomes Je1, this becomes Je2, this becomes Je3, and this becomes Je4. Because of the 2 pi. It changes them to different spots, and that's it. So you can think of these as the first cover description for structure. And then when you connect to the second level of this double cover, then you have an extra twist put in, which transforms these to the j's. This one is squared, it's a 2-dimensional. That one's squared, it's a 2-dimensional. And Je3 and Je4 are 2-dimensional. They literally are just transformed into them. Okay, so both sides, this one without the 2 pi directly connects. And then we have to add the 2 pi to be one step away for the real structure we're interested in, to the hyperbolic figure 8 knot. And this one, and that's because we're going to the double layer, right? It's like the hyperbolic figure 8 knot plus an extra twist to get to the next layer of the same logical construction. We just added a twist into it, that's all. And this side also connects the same logic. Algebraically, it's a really nice, simple story. You can tell you've only had to modify by one twist, one internal loop that you've put into this component. And we have to hold this gap in our hyperbolic structure. It needs to be of this specific size. That's kind of theoretically where we're at. What we're trying to do then, we're in a unique spot where we have all the claims of the constants of nature. Right or wrong, we actually have claims that give us the right outputs, okay? And the ones that are right, therefore, are clues that no one's ever seen before about the coherent logic of transforms allowed to the minimal arena. But I should note, using logarithms to structure your system, beautiful. That's the best you can do. E's and logs, the best structure you can get together. But these are completely closed, connected structures, and they use only ones, right? The magnitude of I is 1, the magnitude of that guy is 1, a 1 here, a 1 there. Yeah. We literally have 4 ones here, just at different directions. So we have connections between 4 ones bound anti-symmetrically here, with logarithmic structure. It's really, really kind of a beautiful idea, but it's also unitarily. This is like, here's the unit circle. This is the unit manifold. See the units? I also should note that the power tower on column 3, I think literally is the energy structure, or the Hamiltonian structure projected from this. So defining the constant levels of, or the surfaces of energy that are associated to every particle. I think it's literally just that column. And that column's held together on the inside just by the power towers. The eye to 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 the eye the whole way. We partition into certain many sheaths, certain many layers where there's then some shape that extends from it that defines a constant energy, a surface of constant energy. But then there'll be another layer above. So there's the way to get from layer to layer. I mean, the layers themselves are all logicked by the eye to 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 the eye power tower. That's the interesting thing. So I think this is the logic for the transform along that structure. So far, the story is incredibly short, and I have to really emphasize, it's not just that we found a manifold that connects the logic of the constants of nature, the measured features. We found the simplest manifold. This is really a good reason to suspect that this is the right way to go.
It's okay. So you're saying that it not only is like a manifold that does that, but it also is the simplest manifold you can come up with.
Yes. It's not just that you can come up with some complex manifold that happens to perfectly satisfy these numbers. No, it's that we found the one that does it is the simplest one. Yeah, it's huge. Which means that
really stupid
physics and geometry are completely married.
Yeah.
So what it really means is completely married in a much richer way than anyone ever really thought. Here's our geometric story. Responsible for all the transforms available to chemistry. That's huge, okay? It can be in a very condensed form. And the geometric parameters of this story are all ones. It's a gorgeous, gorgeous story. Okay, so let's take that story and see how far we can leverage it, how much we can get out of it is the goal. But in that story, the pattern that led us to the story, we also have all those 288 prescriptions for a transform that can be done to the structure. So all of those are compatible ways to transform, or different, unique ways to transform the structure. So now our goal is to look into all these structural components that are all new clues. Because up until now, the constants of nature were complete mysteries and they weren't part of a geometric story. Now we have a geometric story. We got pattern. We have something to make sense of. It's like in history, Kepler observed data from generations of where the positions of the planets were at certain times. So they recorded the time, hopefully really accurately, right? And the position, hopefully really accurately. But over generations, he got some patterns that he could find in the data. So that's really cool. He saw that there are patterns.
Yeah.
That's one step. It's like that. We found there are patterns. And what really was exciting is when Newton came along with a set of concepts that logically lead to those patterns. Okay, so he could derive the reason behind that pattern. But he was looking for it because he knew about Kepler finding the patterns.
Yeah.
So anyway, that's the stage we're in right now. We have found a pattern that links all 288 constants. We've got a story that's developing very coherently about what the pattern means, but we're not done with it yet. So we're still trying to understand that story, and I mean, we know we're done when we understand it so well that we can mechanically interface with the story.